Your engine makes power, but your engine doesn't move the car, not directly. Between your engine and your wheels, there's a box full of gears, shafts, clutches, fluid, and engineering that most people never think about until it breaks, and then they think about it constantly, because a transmission replacement costs more than some people's cars. The transmission is one of the most mechanically complex components in your vehicle. It takes the engine's rotational output and translates it into the right speed and force for whatever you're doing. Crawling through a parking lot, merging onto a highway, climbing a mountain, or sitting in traffic going absolutely nowhere. Without it, your engine would spin uselessly. With it, you have a machine that can operate across an enormous range of speeds and loads using an engine that only works well within a narrow band of RPMs. There are 4 main types of transmissions in modern cars: manual, traditional automatic, CVT, and dual clutch. They all do the same fundamental job. They all solve the same physics problem, but they do it in completely different ways. And those differences affect how the car feels, how it performs, how efficient it is, how reliable it is, and how much you'll cry when it needs repair. Let's open the box. To understand transmissions, you first need to understand the problem they solve, and the problem is simple. Your engine is bad at its job. Not bad in a quality sense, bad in a range sense. An internal combustion engine produces useful power only within a limited RPM range. Below a certain RPM, the engine doesn't make enough torque to move the car. Above a certain RPM, the engine hits its red line and risks damage, the sweet spot. The range where the engine makes good torque and good horsepower is typically a band of maybe 2,000 to 3,000 RPM wide out of a total range of 0 to 7,000. But driving requires an enormous range of wheel speeds. You need the wheels to turn slowly when you're inching through a parking lot at 3 miles per hour. You need them to turn very fast when you're cruising at 80 miles per hour on the highway. And you need enough force at the wheels to accelerate a 3,500-pound vehicle from a standstill, climb a steep hill, and pass a truck at highway speed. If you connected the engine directly to the wheels with a single fixed gear ratio, you'd have to choose either a ratio that gives you enough force to start from a stop, which would limit your top speed to maybe 30 miles per hour before the engine hits redline, or a ratio that lets you cruise at highway speed, which would mean the engine doesn't have enough torque to get the car moving from a standstill. You can't have both with one ratio. Think of it like a bicycle. A bike with only one gear works fine on flat ground, but try to ride it up a steep hill and your legs don't have enough force to push the pedals. Try to ride it downhill and your legs can't spin fast enough to keep up. That's why bikes have multiple gears: low gears for climbing that give you more force per pedal stroke, and high gears for speed that cover more distance per pedal stroke. Different mechanical advantage, different results. Your car's transmission is the same concept. It provides multiple gear ratios, so the engine can operate in its optimal RPM range regardless of what the wheels are doing. In a low gear, the engine turns many times for each rotation of the wheels. Lots of force, low speed. In a high gear, the engine turns fewer times per wheel rotation. Less force, high speed. The transmission matches the engine's output to the driving situation. It's the translator between an engine that wants to spin at 3,000 RPM and wheels that need to turn at completely different speeds, depending on the moment. A gear ratio describes the relationship between the input speed from the engine and the output speed going to the wheels. A ratio of 3.51 means the engine's crankshaft rotates 3.5 times for every single rotation of the transmission's output shaft. That multiplication works in reverse for torques. The output torque is 3.5 times the input torque, minus friction losses. First gear has the highest numerical ratio, typically 3.0.1 to 4.5.1. The engine spins fast. The wheels turn slowly, but the torque at the wheels is multiplied significantly. This is what gets a heavy car moving from a dead stop. It's the low gear on a bike. Lots of force, slow movement. Top gear has the lowest numerical ratio, often 0.6.1 to 1.0.0. Some top gears are overdrive ratios below 1,001, meaning the output shaft actually spins faster than the crankshaft. This keeps engine RPM low at highway speed, which improves fuel economy and reduces engine wear. It's the tall gear on a bike, less force per pedal stroke, but you're covering a lot of ground. The gears between first and top fill in the gaps, creating a series of steps that let the engine stay within its efficient RPM range as the car accelerates from 0 to highway speed and beyond. A 6-speed transmission has 6 ratios, an 8-speed has 8, a 10-speed has 10. More gears means smaller steps between ratios, which means the engine stays closer to its optimal RPM at all times, which means better efficiency and smoother power delivery. After the transmission, the output goes through the differential, which has its own fixed ratio, typically 2.51 to 4.51, that further multiplies torque before it reaches the wheels. The total multiplication at any moment is the transmission ratio times the differential ratio. In first gear, with a 3.51 transmission ratio and a 3.73.73 show, the engine's torque is multiplied by roughly 13 before it reaches the axle. That's why even a modest engine can chirp the tires in first gear. The manual transmission is the simplest and oldest type. It's also the one that puts you in complete control of the gear selection. You choose the gear, you operate the clutch, you decide when to shift. The car does nothing automatically. Inside a manual transmission, there are 2 main shafts running parallel to each other. The input shaft, connected to the engine through the clutch, and the output shaft, connected to the drive shaft and eventually the wheels. Each gear ratio is created by a pair of gears, one on the input shaft and one on the input shaft, of different sizes. The different size combinations create different ratios. When you move the shift lever, you're mechanically engaging a selector fork inside the transmission that slides a synchronizer sleeve into position, locking one pair of gears to the output shaft. Only one pair can be engaged at a time. Moving the lever to a different position disengages the current pair and engages a new one. The clutch is the mechanism that connects and disconnects the engine from the transmission. It's a friction disc, the clutch disc, sandwiched between the engine's flywheel and a pressure plate. When you press the clutch pedal, the pressure plate releases. The clutch disc separates from the flywheel, and the engine is disconnected from the transmission. This allows you to shift gears without the engine's rotation fighting the gear change. When you release the clutch pedal, the pressure plate clamps the clutch disc back against the flywheel, reconnecting the engine to the transmission. The synchronizers are critical components that most people don't know about. When you shift from one gear to another, the gear you're engaging is spinning at a different speed than the output shaft. If you just rammed the gears together at mismatched speeds, you'd hear a horrible grinding noise and damage the teeth. Synchronizers are cone-shaped friction devices that gradually match the speeds of the gear and the shaft before they lock together. They're the reason modern manual shifting feels smooth instead of violent. When synchros wear out, from aggressive shifting, poor technique, or age, shifts become notchy, difficult, or accompanied by grinding. That's the transmission telling you the synchros are dying. Manual transmissions are mechanically simple compared to automatics. Fewer moving parts means less to go wrong, lower manufacturing cost, and cheaper repairs when something does fail. They're also lighter, which helps performance and fuel economy, and they give the driver complete control over gear selection, which many enthusiasts value for the engagement and connection it provides. The downside is the learning curve and the inconvenience in stop-and-go traffic. Operating a clutch pedal in heavy traffic for an hour is physically tiring and mentally tedious. This is the primary reason manuals have nearly disappeared from the mainstream market. Most buyers simply don't want to deal with it. In some markets, manuals represent less than 2 to 3% of new car sales. But for driving enthusiasts, the manual transmission remains a deeply satisfying mechanical interface. The physical act of shifting, the clutch engagement, the click of the lever into the next gate, the rev match on a downshift, creates a connection between the driver and the machine that no automatic can replicate. It's the difference between playing a video game with a controller and playing a musical instrument. Both produce output. One involves you in the process. The traditional automatic transmission, also called a torque converter automatic, is the one in most cars on the road today, and it's significantly more complex than a manual. The key difference: there's no clutch pedal. Instead of a friction clutch connecting the engine to the transmission, an automatic uses a torque converter, a fluid coupling device that transfers power from the engine to the transmission through hydraulic fluid. The torque converter is a sealed donut-shaped housing filled with transmission fluid. Inside are three main components: the impeller, driven by the engine, the turbine, connected to the transmission input shaft, and the stator, a stationary element that redirects fluid flow to multiply torque. When the engine spins the impeller, it flings transmission fluid outward into the turbine. The moving fluid pushes the turbine, which turns the transmission input shaft. The stator sits between the impeller and turbine and redirects the returning fluid to reinforce the impeller's rotation, which multiplies the torque. At low speeds, a torque converter can multiply engine torque by a factor of 1.5 to 2.5. This multiplication is why automatics feel strong at launch even without the driver managing a clutch. Think of it like two fans facing each other. Turn one fan on. It blows air at the second fan, which starts spinning from the airflow. That's basically how a torque converter works, except with fluid instead of air, and with a stator that makes the process more efficient. Because the connection between the engine and transmission is fluid rather than mechanical, there's always some slippage. The turbine never spins quite as fast as the impeller. This slippage is what makes automatics feel smooth but also costs efficiency. To combat this, modern automatics have a lockup clutch inside the torque converter that mechanically locks the impeller and turbine together at cruising speeds, eliminating slippage and improving fuel economy. The lockup clutch engages when the engine and transmission are at similar speeds and disengages when you need the torque multiplication again, like during acceleration. Inside the transmission itself, automatic gearboxes use planetary gear sets instead of the parallel shaft gear pairs found in manuals. A planetary gear set consists of a central sun gear, a ring gear around the outside, and planet gears in between that are held by a carrier. By holding different elements stationary and allowing others to rotate using clutch packs and bands controlled by hydraulic pressure, the transmission achieves different gear ratios from the same set of gears. It's elegant, compact, and allows for a large number of ratios in a relatively small package. Modern automatics have gotten remarkably good. 8, 9, and 10-speed automatics shift faster than any human can, optimize for fuel economy with narrow ratio spacing, and can be nearly imperceptible in their shift quality. The ZF 8-speed automatic, used by BMW, Chrysler, Audi, and many others, is widely considered one of the best transmissions ever made, with shifts so smooth and quick that even manual transmission purists grudgingly respect it. The drawback of traditional automatics is complexity. More moving parts, more hydraulic circuits, more control valves, more potential failure points. When an automatic fails, the repair is expensive, often $3,000 to $6,000 or more for a rebuild. They're also heavier than manuals, which hurts performance and efficiency slightly. And despite their improving shift speed, they still can't match the immediacy and directness that a skilled driver feels through a manual. Most modern automatics offer some form of manual control. Paddle shifters behind the steering wheel, or a sequential sport mode on the shift lever that lets the driver command upshifts and downshifts. This doesn't make the automatic a manual. The computer still controls the clutch engagement, still protects the engine from over-revving, and still overrides the driver's commands if you do something stupid like try to downshift into first gear at 80 miles per hour. But it does give you some influence over gear selection when you want it. Attacking a mountain road, passing on a 2-lane highway, or just having fun, while letting the transmission handle everything automatically the rest of the time. It's the best of both worlds compromise that has made the traditional automatic the dominant transmission type worldwide. The continuously variable transmission is the one that car people love to hate. And some of that hate is earned, but some of it is based on misunderstanding what a CVT is designed to do. A CVT doesn't have fixed gears at all. Instead, it uses two conical pulleys connected by a steel belt or chain. One pulley is connected to the engine, the other to the output. Each pulley can change its effective diameter by moving its two halves closer together or farther apart. When the halves squeeze together, the belt rides higher on the cone, creating a larger effective diameter. When they spread apart, the belt rides lower, creating a smaller diameter. By continuously adjusting the diameters of both pulleys simultaneously, the CVT creates an infinite number of gear ratios between its lowest and highest settings. There are no discrete steps, no shifts, just a smooth, continuous change in ratio that keeps the engine at whatever RPM is most efficient for the current driving situation. From a pure efficiency standpoint, this is brilliant. A CVT can hold the engine at its most fuel-efficient RPM point, while the car accelerates smoothly through any speed. Traditional transmissions have to step through fixed ratios, which means the engine RPM jumps up and down with each shift. The CVT eliminates those steps, keeping the engine in its sweet spot at all times. And here's where the hate comes from: the driving experience. When you accelerate in a CVT-equipped car, the engine revs to a certain RPM and stays there while the car accelerates. There's no upshift, no RPM drop, no shift point, just a constant drone as the CVT adjusts the ratio underneath you. This is called the rubber band effect, because it feels like the engine is revving, but the car is responding with a delay. The engine screams at a high RPM while the car slowly gains speed. It's deeply unsatisfying for anyone who's used to the rhythm of a conventional transmission. Some manufacturers have addressed this by programming virtual gears or stepped ratios into their CVTs, artificial shift points that mimic the feel of a conventional automatic. Even though the twatter mechanical structure is continuously variable, the transmission will hold a ratio, then shift to the next one, with a simulated RPM drop. It's a software illusion designed to make the CVT feel more conventional. Some implementations are convincing, others feel artificial. Subaru's CVT with simulated 8-speed mode and Toyota's direct shift CVT, which adds an actual mechanical first gear for launch and then transitions to the CVT for the rest, are among the better implementations. CVTs excel in one area: fuel economy in normal driving. For commuters, rideshare drivers, and anyone who prioritizes miles per gallon over driving excitement, a CVT does its job quietly and efficiently. Several of the highest MPG non-hybrid vehicles on the market use CVTs. They're lighter than comparable automatics, mechanically simpler, fewer parts, and optimize engine efficiency better than any fixed-gear transmission. The reliability question is the other source of CVT skepticism. Early CVTs had significant durability issues: belt slippage, overheating under sustained load, and premature failure. Modern CVTs have improved substantially, particularly from manufacturers like Toyota and Subaru, who've invested heavily in the technology. Nissan's CVTs, particularly in certain model years, have had a rockier reliability reputation that has colored public perception of the entire technology. CVTs are generally not recommended for towing, aggressive driving, or high-torque applications. The belt and pulley design has inherent torque limitations compared to gear-based transmissions. Manufacturers that pair CVTs with high-performance engines or put them in vehicles that owners might tow with are often fighting against the CVT's fundamental mechanical constraints. The dual-clutch transmission, DCT, also called DSG, Volkswagen's term, PDK, Porsche's term, or PowerShift, Ford's term, is the engineer's answer to a question nobody asked until they saw the answer. What if we made a manual transmission that shifts itself faster than any human ever could? A DCT is essentially two manual transmissions in one housing, each with its own clutch. One clutch handles the odd gears: first, third, fifth, seventh. The other clutch handles the even gears: second, fourth, sixth, eighth. When you're driving in, say, third gear, the odd gear clutch is engaged in transmitting power. Meanwhile, the even gear side has already pre-selected fourth gear and is just waiting. When it's time to shift, the odd gear clutch opens and the even gear clutch closes simultaneously. Power transfer is nearly instantaneous. Shift times are measured in milliseconds, often faster than 100 milliseconds. There's almost no interruption in power delivery. Think of it like having two hands on two different light switches. One light is on, current gear. The other is ready, next gear. To switch, you flip one off and the other on at the same time. The room never goes dark. That's how a DCT shifts. The power flow to the wheels is essentially continuous. The result is a transmission that combines the efficiency of a manual. There's no torque converter wasting energy through fluid slippage, with shift speeds that exceed even the best automatic. DCTs can be operated in full automatic mode, where the computer decides when to shift, or in manual mode via paddle shifters behind the steering wheel, where the driver commands each shift with a flick of the finger. On the performance end, DCTs are spectacular. Porsche's PDK is widely regarded as one of the finest transmissions ever engineered. Volkswagen's DSG has been a staple of the GTI and Golf R for years. Ferrari, Lamborghini, McLaren, and BMW M cars all use or have used dual-clutch transmissions because the shift speed and efficiency are unmatched. But DCTs have weaknesses, and they're significant in certain contexts. Low-speed behavior. Because DCTs use friction clutches instead of a torque converter, they don't have the smooth, slipping fluid coupling that makes torque converter automatic so civilized at low speeds. In stop-and-go traffic, some DCTs can feel jerky, hesitant, or unsure. The clutches engaging and disengaging in tight quarters can produce shuddering, lurching, and a general feeling of unease. This is especially true of dry clutch DCTs, less expensive designs that use clutch packs without oil cooling. Dry clutch DCTs are more affordable, but less smooth and less durable than their wet clutch counterparts, which run the clutch packs in oil for better cooling and smoother engagement. Reliability concerns. Some DCTs, particularly dry clutch designs, have had significant reliability issues. Ford's power shift dual clutch transmission used in the Fiesta and Focus became the subject of class action lawsuits due to widespread shuddering, premature clutch failure, and poor low-speed behavior. Volkswagen's dry clutch 7-speed DSG also had early reliability concerns. Wet clutch DCTs tend to be more durable, but are also more expensive. Not ideal for towing or heavy loads, DCTs are designed for quick shifts and efficient power delivery, not for the sustained high-torque, low-speed operation that towing demands. The clutch packs can overheat under heavy, sustained loads. The DCT is a performance-focused technology that makes some compromises in daily livability. In a sports car or a hot hatch where the driver values shift speed and engagement, it's outstanding. In a family commuter car where smoothness and low-speed refinement matter most, it's not always the right tool. This is the question everyone wants answered, and the answer, as always, is that it depends on what you value and how you drive. Choose a manual if you love driving engagement, want the most direct connection to the car, enjoy the physical act of shifting, primarily drive for pleasure rather than commuting, and don't mind the inconvenience in traffic. You'll get the simplest, lightest, cheapest to repair transmission with full driver control. The manual is dying in the market, but it's alive and well in the hearts of anyone who's rev-matched a perfect downshift into a corner. Choose a traditional automatic if you want the most refined, do-everything daily driving experience. Modern 8 to 10 speed automatics are incredibly smooth, reasonably efficient, and can handle everything from rush hour traffic to highway cruising to towing. They're the default for a reason. They do nothing badly and most things well. If in doubt, this is the safe choice. Choose a CVT if fuel economy is your top priority and driving excitement is not. For commuting, city driving, and maximizing miles per gallon, a CVT from a reputable manufacturer is an excellent tool. Just don't expect it to feel exciting. It's an appliance, a very efficient, very practical appliance. Choose a DCT if performance matters and you're willing to accept some low-speed compromises. In a sports car or performance application, a DCT delivers shifts that make you feel like a racing driver. In a commuter car, it can feel awkward and unsettled. Match the tool to the task. None of them is objectively superior. They're all solutions to the same fundamental physics problem, matching engine output to wheel demand, engineered with different priorities. The best transmission is the one that matches your priorities. Regardless of which type you have, the transmission relies on fluid to function. Manual transmissions use gear oil. Automatics use automatic transmission fluid, ATF. CVTs use CVT-specific fluid. DCTs use their own formulation. The fluid lubricates, cools, and, in automatics and DCTs, acts as the hydraulic medium that actuates clutches and controls gear changes. Transmission fluid degrades over time. It oxidizes, loses its friction properties, and accumulates contaminants. Old, degraded fluid leads to rough shifts, increased wear, overheating, and eventual failure. A transmission fluid change, typically every 60,000 to 100,000 miles depending on the manufacturer and driving conditions, is one of the cheapest forms of insurance against one of the most expensive repairs on the car. Some manufacturers claim their transmission fluid is lifetime fill, meaning it never needs to be changed. Many independent mechanics and transmission specialists disagree strongly with this claim. Lifetime often means the lifetime of the warranty, not the lifetime of the car, if you plan to keep your car past 100,000 miles, which most people do. Changing the transmission fluid is one of the smartest maintenance investments you can make. It costs a few $100s. A transmission replacement costs several thousand. The math is clear. Use the correct fluid for your transmission. ATF, CVT fluid, and DCT fluid are not interchangeable. Using the wrong type can damage clutch packs, degrade seals, and cause erratic shifting or outright failure. Check your owner's manual, use the specified fluid, and don't let a quick lube shop put generic ATF in your CVT. Transmissions rarely fail without warning. They send signals for weeks or months before they give up completely. Knowing those signals can save you from a roadside breakdown and give you time to address the problem before it becomes catastrophic. Slipping. The engine revs higher than normal, but the car doesn't accelerate proportionally. It feels like the transmission is momentarily disconnecting from the engine and then re-engaging. In an automatic, this might feel like the car briefly loses power during acceleration. In a manual, the clutch might be slipping, the engine revs climb, but the car doesn't respond, especially in higher gears under load. Slipping is one of the earliest and most common signs of transmission wear. Delayed engagement. You shift from park to drive or reverse, and there's a noticeable pause, 1 to 3 seconds, before the transmission engages and the car starts to move. The healthy transmission engages almost immediately. A delay indicates low fluid pressure, worn clutch packs, or internal seal degradation. Harsh or rough shifts. Instead of smooth, nearly imperceptible gear changes, the shifts feel like clunks or bangs. The car jerks forward with each upshift. Downshifts are accompanied by a thud. This can indicate worn clutch packs, failing solenoids, degraded fluid that's lost its friction properties, or electronic control issues. Fluid leaks. Transmission fluid is typically red or pink when new and turns darker brown with age. If you see red or brown fluid spots under your car, typically near the center or front, your transmission is leaking. Low fluid levels lead to overheating, poor lubrication, and accelerated wear. A transmission leak caught early is a cheap seal repair. A transmission run dry is a total rebuild. Strange noises, whining, buzzing, or humming that changes with vehicle speed, not engine speed, often points to the transmission. A grinding noise when shifting a manual means the synchros are worn. A clunking sound from the undercarriage during shifts in an automatic suggests worn internal components or a failing mount. Burning smell. Overheated transmission fluid has a distinct burnt odor. If you smell it, especially after towing, climbing long hills, or driving in heavy traffic, your transmission is running too hot. Overheating is the #1 killer of automatic transmissions. It degrades the fluid, damages seals and clutch packs, and warps internal components. If you smell burning transmission fluid, stop driving and let it cool. Check engine light or transmission warning light. Modern transmissions are monitored by the engine control module. If the computer detects abnormal behavior, erratic shift patterns, unusual slip, temperature spikes, it sets a diagnostic trouble code and illuminates a warning light. Don't ignore it. Scan the code and address the problem before a computer warning becomes a mechanical failure. If you catch these symptoms early, many transmission problems can be addressed with fluid changes, solenoid replacements, or minor repairs that cost hundreds rather than thousands. Ignore them, and the problem compounds until the transmission needs a complete rebuild or replacement. One of the most expensive repairs on any vehicle. Electric vehicles are fundamentally changing the transmission conversation. Most EVs use a single-speed reduction gear, one fixed ratio, because electric motors produce usable torque from 0 RPM all the way to their maximum speed. There's no narrow power band to manage. There's no need for multiple ratios to keep the motor in its sweet spot, because the sweet spot is nearly everywhere. This is a massive simplification. No gear changes, no clutch packs, no torque converter, no planetary gear sets, no synchronizers, no transmission fluid to degrade. The single-speed reduction gear is small, light, efficient, and essentially maintenance-free. It's one of the reasons EVs have lower maintenance costs. The most complex mechanical component in a traditional car simply isn't there. Some high-performance EVs are experimenting with two-speed transmissions to optimize both launch performance and top-speed efficiency. Porsche's Taycan uses a two-speed on the rear axle, but for the vast majority of electric vehicles, one gear does the job. As EVs gradually replace internal combustion vehicles over the coming decades, the multi-speed transmission, one of the most intricate mechanical devices ever mass-produced, will slowly fade from the automotive landscape. Future generations of drivers may never experience the rhythm of an upshift, the snap of a paddle, or the satisfaction of a perfectly riv-matched downshift. The transmission, like the carburetor before it, will become an artifact of a mechanical era that's giving way to an electrical one. Whether that's progress or loss depends entirely on what you value. The engineer sees efficiency gained. The enthusiast sees connection lost. Both are right. Transmissions exist because engines only work well in a narrow RPM range, but driving requires a huge range of wheel speeds. Gear ratios multiply engine torque in low gears for starting power and reduce multiplication in high gears for highway speed. Manual transmissions use parallel shafts, synchronizers, and a driver-operated clutch. Simple, engaging, full control. Traditional automatics use a torque converter and planetary gear sets. Smooth, refined, the do-everything default. CVTs use variable diameter pulleys and a belt for infinite ratios. Maximum efficiency, minimum excitement. Dual-clutch transmissions use two clutch packs and pre-selected gears for near-instant shifts. Performance-focused with low-speed compromises. No type is objectively best. Each prioritizes different things. All transmissions rely on fluid that degrades over time. Change it on schedule or pay for a rebuild. Your transmission is the unsung translator between your engine and your wheels. It's working every second you drive, selecting ratios, managing forces, absorbing the gap between what your engine wants to do and what the driving situation demands. Most people never think about it. Most people never maintain it. And then most people are shocked when it fails and the repair bill has 4 digits. Now you know what's inside the box. You know why it's there. You know how each type works and what it's good at. And you know the one maintenance item, fluid changes, that can keep it alive for hundreds of thousands of miles. If this video finally explained the difference between those 4 transmission types, or settled an argument you've been having, hit like. Drop your transmission type in the comments so we can see how the audience splits between the manual diehards and the automatic realists. And subscribe so you stop pretending to know what DCT stands for when someone says it at a car meet. Later.